So this week we're gonna finish off chapter 13. By Wednesday, you'll know pretty much everything that you'll need to know for the first exam. So the first exam is gonna be Friday of next week. So you still have like a little bit less than 2 weeks. But again, by Wednesday, we'll cover everything that you need to know. So it's like the exam technically is chapters 11, 12, and 13. But it's really just going to be over chapters 12 and 13. Chapter 11 was just like what we're doing now, except those in 2 dimensions. So you really just need to know chapters 12 and chapter 12 and chapter 13. Yeah, and then I guess I'll say more about the first midterm as we get closer to the due date. But you really should be focusing on chapter 12. That's where most of the points are going to come from. Chapter 13, there's like a couple of ideas that will show up, namely curvature, which we might get to today, and I guess normal vectors, but most of the points are going to come from chapter 12. So I'll say more about the first exam as we get closer to the date. And we'll have 2 days of review next week. So you'll have plenty of time to study in class as well. Okay, so before going over or continuing chapter 13, there's one homework problem I wanted to go over, namely because it uses some knowledge of differential equations to solve it. And I think there are some professors last semester teaching Calc 2 that didn't go over differential equations. So I thought it's probably a good idea I go over this problem. So this is a homework problem. It asks you to find the solution of the differential equation given by r prime of t is equal to 7 times r of t, where the initial condition is given by r of 0 is equal to 694. And so you want to solve this differential equation where you have that the derivative of your vector is proportional to the original vector function that you have. And so this is something we did in Calc 2 last semester, if you had me in the class. How you would go about solving this differential equation is we start off with r prime of t is equal to 7 times r of t. And what you want to do is you want to solve for r of t, which means you're going to have to take an integral, right, to undo the derivative that we have here. And so we're going to divide both sides by r of t to get r prime of t over r of t is equal to 7. And then you want to integrate both sides with respect to t, right? So this is the integral of r prime of t over r of t dt is equal to the integral of 7 dt. And so to solve the integral on the left, right, the one on the right is just a constant. It's just going to be 7t plus some constant vector. But on the left, if we want to solve this integral, we use u substitution, where we're just going to let u be equal to r of t, which then implies that du is equal to r prime of t dt, which is exactly what we have in the numerator. And so you can see that this integral ends up just being equal to the natural log of r of t. So this ends up giving you the natural log of r of t ends up being equal to 7t plus c. And you should be keeping in mind that we're doing things over vectors, like we're doing things in R3. So instead of just having like a constant c, this should really be a vector. This should be like c1, c2, c3. Because we're in 3 space, right? The vector we started off here was in 3 space. And so all we need to do is just solve for r of t, which means just exponentiating both sides with respect to base e. If you exponentiate both sides, this is going to tell you that r of t is equal to e to the 7t plus c1, c2, c3, this vector. This is a trick we did a couple of times last semester. This is the same thing as doing e to the 7t multiplied by e to the c1, c2, c3. And then this itself is just a constant vector, right? So you can rewrite this as being equal to some vector of constants a1, a2, a3 multiplied by e to the 7t. right? So if you bring down, like we said, R of t is equal to this that we have here. So just bringing down the R of t, this is the same as saying R of t is equal to what we have here. And so to determine what A1, A2, and A3 are going to be, you just use this initial condition, right? So when t is equal to 0, we have R of 0. This is equal to 6, 9, 4. This is also just equal to the vector A1, A2, A3 times e to the 0th power, which is just equal to 1, right? And so this ends up just being, I think this just tells you what the constants are immediately. You don't have to do any solving. You just see A1 ends up being equal to 6, A2 ends up being equal to 9, and then A3 ends up being equal to 4. So combining those pieces of information, we get R of t is going to be equal to 6, 9, 4 times e to the 7t, which you can also just write as being the vector 6 e to the 7t, 9 e to the 7t, and then wait, was it? Oh, it was 4. It looks like a 7 the way I wrote it. So that's what I was getting confused over. Not 7, 4 times e to the 7t. I need more. This kind of looks like a 2. I need more careful. Yeah, so this is what the answer looks like. And you can note, like, if you see this problem on the homework and you haven't done it already, all you're really doing is, like, it's telling you have 7 here. So that's like where the 7 shows up in your answer. And then you have 6, 9, 4, which shows up as, like, the constants. So, I mean, there's, like, an easy way of generalizing the solution of this is what I'm saying. Because, like, it's going to change what this number is going to be, and it's probably going to change the initial condition. But if you look at the final answer here, it's easy to change and adjust your answer, right? Okay, so that's the homework problem I wanted to go over. Again, the homework's due tonight at 11:59. And then because there's an exam next week, the next homework will be due 2 weeks from today. So it still exists. It's just due 2 weeks from today. The priority over the weekend should be working over the exam review. I'll be sending out on Wednesday. Yeah, any questions about this homework problem? And if you have any other problems regarding the homework, I'll be in my office from 2 to 4 today. So there's plenty of availability, or you can just email me. But it seems like this homework should be okay. It's mostly just computing derivatives and integrals of vectors, which is really just the same as doing derivatives and integrals of like single variable functions. So it shouldn't be too bad. And there's only 15 problems, so I took it easy on it. Okay. Yeah, so this is I think we finished everything in section 13.2. Let me make sure. I'm pretty sure we did. I think we completely finished the packet. Okay, yeah, so we're on section 13.3. This is kind of a repeat in the sense that we're looking at arc length and speed again. This is a second thing we talked about in the semester, right? Except we were doing things in R2 instead of R3. But what we're going to see is that the generalization, like going from R2 to R3, like 2 dimensions to 3 dimensions, it's pretty much the same idea. The equations are pretty much the same. Things work out the way you expect them to. So I'm not going to spend a lot of time, or really any time, deriving the following equation. Should recognize it as what we've already done and just kind of be like, oh yeah, it makes sense. We just add z prime squared. Right, so what do I want to say? Yeah, so just briefly mentioning that the equation for arc lengths in R3 generalizes the previous equations we've looked at in a natural way. So the arc length formula we're going to be using today and tomorrow is given by the following. So we're going to assume that R of t is some sort of like vector valued function that ends up traversing some parametric curve C that ends up being parameterized by the domain. So t is between A and B. So we're going to assume that R prime of t exists and is continuous. Then the arc length S of our curve C is equal to the following. So arc length is denoted by S, and it's the integral from A to B of the length of the velocity vector. So you take your parameterization, your like vector valued function, you take its derivative, and then you compute the magnitude, and then you take the integral. And so that ends up just giving you the explicit formula of computing the integral of the square root of x prime of t squared plus y prime of t squared plus c prime of t squared. And so we saw this, maybe it's unnecessary for me to do this, right? This is from the first week of class, right? We had this was the arc length formula. They're the exact same, except now we have a plus c prime of t squared. So it isn't really anything that new. We just have like this extra part that we're adding inside, right? And so we'll just go through a quick example before we go a little bit deeper with this idea. And so for this example, it wants you to find the arc length s of the helix given by r of t is equal to cosine of 3t, sine of 3t, and then 3t, where we're assuming that t is bounded between 0 and 2 pi. And so you just plug into the formula, right? I guess we'll just, before we do anything, we'll just note that we have the following. So r prime of t, this is equal to minus 3 sine of 3t by the chain rule. Then this is going to be 3 cosine of 3t, again by the chain rule. And then the derivative of the third component is just given by 3. And so we want to integrate the magnitude of this vector. And again, this is the velocity vector, right? You're just taking the derivative, or I should say it's like the tangent vector, which ends up being a vector that points in the direction of the velocity. I think I'll actually say more about that later. But you want to integrate the magnitude of this vector. So you just compute the magnitude, right? So this is going to be equal to the square root of minus 3 times sine of 3t squared plus 3 times cosine of 3t squared. And then that's going to be plus 3 squared. And so the big idea here, as we've seen plenty of times already in this class, is you're going to have a sine squared plus a cosine squared. So that's just going to become 1. And then this is going to become like 9, and then like plus 9. So you factor out like a 3 squared from like the sine squared plus cosine squared. And you end up getting that this is just equal to the square root of 18. Which is the same thing as doing 3 times the square root of 2. So we just end up getting a constant, right? So the magnitude of this vector, the length is just a constant number. And so the arc length is easy to compute if we're just integrating a constant. So the arc length, this is the integral from 0 to 2 pi of the magnitude of the derivative of your vector. We just computed that this magnitude is equal to 3 times the square root of 2. So this is 3, the integral of 3 times the square root of 2 dt. And so to integrate this, this is just a constant, right? So the antiderivative of this is 3 times the square root of 2 times t. And then you plug in t is equal to 2 pi and subtract what you get when you plug in t is equal to 0. And this is just going to give you 2 pi times 3 times the square root of 2. And then you can multiply the 2 and the 3 to get that this is 6 pi times the square root of 2. Okay, so this shouldn't be anything too crazy. At the end of the day, you're just finding the magnitude of the derivative and then integrating it. So it isn't anything too bad, usually. I mean, there are examples that are bad, but this one's not terrible. Any questions about this example or this computation? Okay, yeah, and so we're going to be interested in the arc length, namely in order to compute curvature, at least in order to introduce the idea of curvature. And so like how this is going to work is it turns out to understand curvature, you kind of have to take a parametric equation and then you need to reparameterize it in terms of this new variable s, where s is the arc length. The reason why we do that is if you reparameterize a curve in terms of s, the magnitude of the derivative is always going to end up being equal to 1, right? So the magnitude never changes. The only thing that changes is going to be the direction, right? Never the magnitude. Right, so that's something I'll talk about a little bit more. I'm getting ahead of myself a little bit. But to make sure like this whole process works of like reparameterization via the arc length, we're going to first define an arc length function. So by definition, speed is the rate of change of distance traveled with respect to some time t. And so if we wanted to calculate what the speed is going to be, where you should be thinking of speed as being the magnitude of the derivative, or like the magnitude of the velocity vector, we're going to define what's called the arc length function. So you can take this idea of computing the arc length and you can make a function out of it by making it so it relies on t, where the variable t is the upper limit of integration that you have. Right, so this is a function of t, right? This is the arc length is going to change as you change the t value. As t increases, it means that you're considering a larger or like a longer curve, right? Right, so this is the arc length formula. It's, again, just the exact same thing over again, except now the upper limit of integration is a variable. And so if we wanted to calculate what the speed is going to be, again, the speed is just the rate of change of distance traveled with respect to time. So we just take the derivative of both sides of this equation. And if you take the derivative of both sides of this equation, by the second part of the fundamental theorem of calculus, the derivative and the integral are going to cancel out with one another. And so this tells you that the derivative of s with respect to t ends up just being the magnitude of the derivative vector, right? You should be thinking like if you compute the derivative with respect to t at both sides, the integral cancels out and you're just left with what's inside of the integral. So that's like Calc 1 stuff, the fundamental theorem of calculus. And so this relationship provides us with the second of the two important features of the velocity vector given by r prime of t. So it points in the direction of motion, and then its magnitude is given by speed. So like the two things you need to remember regarding velocity is kind of like outlined here. So this velocity vector, v of t, is just equal to the derivative of r of t. So this is maybe this will be confusing when I'm writing things out later on, but if it's bold, that means that's the velocity vector. And then when we talk about speed, speed isn't a vector. Speed is just the magnitude of the velocity vector, right? So it's just a number. And so v of t, right, this is going to be like, if you see this, it's unbolded, which means that we're talking about speed, right? So this is velocity, the velocity vector, and then this is speed. Right, so if it's unbolded, that means it's going to be speed. Usually you just have to rely on context, pretty much. Like when I'm writing, these two things are going to look pretty much the same. But again, this is just the magnitude of the velocity vector. So you need to remember velocity vector, and you need to remember speed for the next couple of parts. And I think this picture, what are you trying to illustrate with this picture? Yeah, so the main thing to take note of is we have two different points on our curve. We have a point r corresponding, or we have a point corresponding to t naught here. And then this is the corresponding velocity vector. Right, and then we have another point r of t1 on our curve, and then this is the corresponding velocity vector. Again, the velocity vector is really just the tangent vector. They're the exact same things as one another. So the thing worth noting at the moment that will show up later is that this vector has a larger magnitude than this vector that we have here. And so if we're thinking in terms of maybe like this is the movement of a particle is what this parametric equation is measuring, the fact that this has a larger magnitude implies that the particle is moving faster at this point than it is at this point. Right, so the larger the velocity vector, or like the larger magnitude of the velocity vector, means that the speed is going to be greater. So it's like moving faster, right? That'll show up later when we talk about this arc length parameterization. Before we do that, I just wanted to go through one more example, just calculating speed. So for this example, with distance measured in feet, it wants you to find the speed at time t is equal to 2 seconds for a particle whose position vector is given by the following. Right, so we have r of t tells you the motion or the position vector of a particle, and this is given by a vector, right? So if you see, again, like t cubed times I minus e to the t times j plus 4 to the t times k, this is the exact same thing as this having the vector t cubed minus e to the t and then 4t. I don't know if this is something that people are getting confused with, like these standard basis vectors, but again, it's just a different way of writing out like this vector in terms of the components. And so if we want to find the speed at time t is equal to 2, we just need to find the magnitude of the velocity. So what it's asking you to do is it's asking you to find the magnitude of the velocity vector at t is equal to 2. And so you can do this just by computing the derivative of this vector, plugging in 2, and then just computing the magnitude. So there isn't really anything tricky. As long as you know this is what you're trying to obtain, as long as you do the calculations correctly, you're not going to mess this up. Right, so r prime of t, this is just the derivative of the components of your vectors. So this is going to be given by 3t squared minus e to the t, and then 4. And so if you plug in t is equal to 2, you're going to get r prime of 2 is going to be equal to, so you plug in t is equal to 2, 2 squared is 4, times 3 will give you 12. You have minus e to the 2. And then 4 is just a constant, so it doesn't really matter. So if you want to find the speed, this is what I was saying before. So I'm writing out the speed. This is v of t. I'm not talking about like the velocity vector. Again, like their notation, when I'm writing it out, it's going to look similar. If I'm saying this is like unbolded v, so this is the speed. This is equal to the magnitude of r prime evaluated at 2. So this is just going to be equal to the square root of 12 squared plus the square of e to the second power plus 4 squared. And so if you put this into a calculator, this is approximately equal to 14.65. And then the units are going to be, like we're calculating the speed, so it's going to be, it's saying we're measuring in feet, and I'm assuming the time is in seconds, so I'll say this is like feet per second. I'm not a major stickler for units on the exam. As long as you get the number, I don't really care about like the units. I just want to make sure you have either this written down on the exam or you have this written down on the exam. Any questions about this example? Yeah, so in a sense, this should be review in that it's really just going over section 11.2 over again. What's going to be new is this following idea of arc length parameterization. So again, this arc length parameterization is going to be important in introducing the idea of curvature in the next section. And curvature is one of the most important ways of quantifying ideas about the curves that you're given. So what does it mean to have like an arc length parameterization? And so in general, there are multiple ways to parameterize a curve. So for instance, if you had the curve r1 of t is equal to t and then t squared, and you had rt of u or r2 of u is equal to u cubed and then u to the 6th power in the second component, these two different curves that we have parameterize the exact same parabola, y is equal to x cubed, right? You can see this by if you let t be equal to u cubed, then like even though they're kind of written differently, they still end up giving you the exact same parabola regardless. So like what this is saying is like you can parameterize the exact same parabola just by using different units, as long as you're smart about how the units relate to one another. And so a way of parameterizing a curve that's going to be useful for us in understanding curvature is going to be to choose a starting point and then travel along the curve at unit speed. So like we want to parameterize the curve such that the speed is always going to just be equal to 1, say like 1 meters per second. And so a parameterization that satisfies this property is going to be called an arc length parameterization, where the parameter is going to be denoted by s. Again, like an intuitive way of thinking about this is when we were talking about s, right? We were saying s is equal to the arc length, right? So that's why we're changing the unit to s, because it's like corresponding to the arc length, right? And so it's going to be defined by the property that I said kind of loosely above, but more formally below. So the speed has constant value 1, which means if we have an arc length parameterization, this means that for all s, we always have that the speed is equal to 1. So the magnitude of the velocity vector evaluated at s always ends up being equal to 1. So this is like the defining property. But there's a couple of other important properties as well if we parameterize our curve using the arc length. Those being that the parameter s corresponds to the arc length of the curve that is traced from the starting point, and thus has the name arc length parameterization. The second bullet point is what I just had written here. So every velocity vector, r prime of s, has length equal to 1. And then the third important property is that the arc length of the curve that is traced over any interval from a to b ends up being equal to b minus a, the length of the interval. And this is it's a quick derivation. You just use the fact that the distance traveled from a to b is given by the following integral. This is the arc length integral. And we know that this quantity is just equal to 1, right? That's the defining property. So you end up just getting that this is equal to the integral from a to b of 1, which is equal to b minus a. And then the second property, you don't really need to know this, but like the intuition, like why, if we have an arc length parameterization, does this end up just being equal to 1? Well, if we have s is equal to the integral from 0 to s of some function like f of t dt, if you take the derivative of both sides of this, let me move this down. Again, this is just for your understanding. It's not going to be super important later on. But if you take the derivative of both sides of this equation with respect to s, this is going to give you that 1 is equal to f of s, like this. Right. And so if you're thinking in terms of arc length, if this is instead like the magnitude of like the derivative or something, then this will tell you the magnitude ends up being equal to 1. That's the intuition behind why the magnitude ends up just being equal to 1 here. Okay. And so there's on the next page, there's like a figure illustrating what I'm talking about. So if you can compare these two curves with one another, the curve that they parameterize, that is parameterized, are the exact same, right? Like they are like the same red line that we have. So like even though we're doing a different parameterization where the left is parameterized by the arc length and the right is parameterized by, I don't know, some other variable t, what changes is just going to be the lengths of the velocity vectors, right? If you compare this image to this image, they're the same aside from the fact that like all these vectors have the exact same length. Whereas the vectors on the right-hand side, like this vector is pretty large, this one's pretty small, this one's kind of in between. Like the velocity or the speed varies over time. It's like the main point. Okay, and so what you're going to be doing on the homework, as well as maybe on the exam, is you need to find an arc length parameterization. And so how do you find an arc length parameterization? There's 3 steps, but really you can just think about it in terms of like the main goal is you're starting off with some parameterization r of t, and you want to transform it so that instead of doing things in terms of t, you want to do things in terms of s. So the first thing you do is step 1. It wants you to form the arc length integral. This gives you a direct way of relating s and t with one another. Like this gives you a way of writing s is equal to g of t. So that's the first step. The second step is it wants you to determine the inverse of g of t. The reason why you want to determine the inverse of g of t is it's going to give you a way of writing t as a function of s. And then the reason why you want to write t as a function of s is once you have t is equal to a function of s, you can just substitute in to your curve, right? Like r is equal to the inverse of g of s, and that will give you a parameterization of the same curve, except now the variable is in terms of s instead of being in terms of t. So like even though like there's 3 different steps and you're thinking like I need to memorize 3 different steps, the ideas are intuitive, right? You relate s and t with one another, you write t as a function of s, and then you substitute t is equal to like this new function in terms of s, right? Those are the main 3 steps here. And this ends up giving you the arc length parameterization. So just as a quick example, for this example, it wants you to find an arc length parameterization of the helix that is traced by the parameterization given by r of t is equal to cosine of 4t, sine of 4t, and then the z component is 3t. So you just follow these 3 different steps, right? So step 1, is you want to compute the general arc length function. So we have S is equal to G of t. This, by definition, is equal to the integral from 0 to t of the magnitude of the derivative. And so the magnitude of the derivative is going to be the square root of the square of the derivative of cosine of 4t. So that's going to give you, say, like 4 sine of 4t squared plus 4 cosine of 4t squared. And then this is going to be plus 3t squared. Not 3t squared, just 3 squared. dt. Right, so all I did was I kind of skipped a couple of steps, but I just took the derivative of this function or this vector valued function, and then I just found the magnitude. Right, and so this is just going to be equal. Again, it's kind of the example we looked at before, right? So this is going to be equal to the integral from 0 to t. If you square this out, you'll get 16 times sine squared, and then that's going to be plus 16 times cosine squared. You factor out a 16, you have sine squared plus cosine squared will just end up being equal to 1. So this is just going to be equal to the square root of 16 plus 9 dt, which is equal to the integral of 5. So the square root of 25 is equal to 5 dt. And so this ends up just being equal to 5t. Right, so this is the arc length formula for S. So you plug in these various values of t and it will spit out this arc length, which is just going to be t times 5. So that's the end of step 1. Step 2, you want to find the inverse of this function. And so what I mean by this, so you kind of have to go back to maybe like algebra 2 or algebra 1, whenever you learned about how to compute the inverse of a function. Right, so we have S is equal to G of t. This is equal to 5t. So if you cut out the middleman and just write out like S is equal to 5t, you have the following. And so all you have to do to find the inverse is you just like, we have S is equal to a function of t. You just want to flip things around. So now that you have like t is a function in terms of S, right? So you solve this equation for t is all you have to do. So that just means divide both sides by 5. That's the only thing that needs to be done. So you end up getting that t is equal to S over 5. And so if you want to use this notation, like they like to write things out as like t is equal to G inverse of S. So we have G inverse of S is just equal to S over 5. So that's step 2. On the homework, there'll be examples that are a little bit more difficult. But at the end of the day, all you have to do is just you take your function, then you just solve for the function like the other variable, right? So you just solve for t. And then the third step, all you have to do now for the third step is you just take your original parameterization, and anywhere you see a t, you just replace it with S over 5, right? So the third step looks like the following. So for step 3, all you do is you take your original parameterization R, and then you plug in G inverse of S. So this is really doing R evaluated at S over 5. And so anywhere you see a t, all you do is just replace it with S over 5. So this is going to be equal to cosine of 4s over 5, sine of 4s over 5, and then you'll have 3 times s over 5, so 3s over 5. Right, so this is the new parameterization you have. This is the parameterization in terms of S, and it should have the property, if you compute the magnitude of this new vector, it should end up being equal to 1, right? So just as a quick check, if you do the magnitude of R prime evaluated at G inverse of S, this will be equal to the square root of, I'm not going to go on in complete detail, but if you take the derivative of this, you'll get 4s over 5 squared, or it'll be 4 over 5 squared that'll give you like 16 over 25 times sine squared plus 16 over 25 times cosine squared. And then this will be plus 9 over 25. Right, so again, this just becomes 1. So you get 16 over 25 plus 9 over 25, which is just equal to 25 over 25, which is equal to 1. This is something you can verify in more detail on your own, but I just wanted to point out, if you compute the derivative of this vector and then you compute the magnitude, it ends up being equal to 1, which is the property we wanted to have, right, in doing this. Maybe I shouldn't, okay, that was like a check. Your answer, this is like the final answer though. Right, on the exam, if I ask you for an arc length parameterization, you just need to get here. You don't have to verify. Yeah. So it shouldn't be too bad, hopefully, getting the arc length parameterization. Any questions about this example? Or just about the idea in general? Okay. Yeah, so I think that's it for section 13.3. Again, the main things you need to remember are like how to compute the arc length, velocity vectors, speed, and then finding the arc length parameterization. Those are all things that will show up later on in these next few sections. Okay, so next we're talking about curvature. In layman's terms, curvature is really just how much a curve is bending, right? So if you have, just as a really quick example, if you have a curve like this, that means it has like a small curvature in comparison to a curve like this, right? There isn't like that much that's curving. It's almost like a vertical line for this example, but if you follow this curve, you can see it's bending pretty completely. So like the curvature is going to end up being higher for this function. And so we want to have like a quantity or some sort of numerical expression that tells you like whether or not you're bending a lot or whether or not it's kind of like vertical or horizontal. And so it's a really fundamental number or value used to study simple like geometric properties of curves and motions along curves. And it has like a ton of different applications. Of course, like you can look at like the roller coaster, like a loop kind of corresponds to like some sort of curvature that you want to have. And then I guess curvature, I don't know anything about like biochemist or anything like that. But I guess people study the effect of curvature on DNA as well. Like these various curvatures, maybe it has like some sort of influence on who you are as a person. I don't know. I don't know anything about biochemistry, but maybe someone's interested in. Anyways, yeah. So a natural way to define curvature based off of this intuition, like if you're thinking about like how much is the graph curving, right? Really, you can kind of understand how much the graph is curving by just looking at these velocity or like these tangent vectors, and then recording the velocity of those tangent vectors, right? If it's not changing direction that much over time, you should expect the curvature to be pretty low. Whereas if like this example, it's changing its direction very drastically. So like you should expect the curvature is going to be high. So that gives you an intuition in terms of like how we're going to be computing the curvature, right? So like a natural way to define curvature is to consider the rate at which the direction along the curve is changing. To indicate the direction along a curve, we make use of the unit tangent vectors. And so what do I mean by a unit tangent vector? Well, we know about tangent vectors and we know how to get a unit vector from any vector. So like, even though this is going to be like a new definition, this is something before even going into the definition, you should be able to understand how to compute. But I'm going to spell it out anyways. So consider a path with parameterization R of t is given by x of t, y of t, and z of t and its components. We're going to assume that the derivative is going to be non-zero for all t in our domain of R of t. And this R of t should be bolded, I guess. It's not like a huge deal, but this should be like a bolded R of t. Like the R of t it mentions here is the same one that it has here. So a parameterization with this property is going to be called regular. I think the word regular might show up on like a homework or two, but it's not going to be like, I'm not going to ask you like on the exam to like define what a regular curve is. It just means that the derivative is non-zero for all t in the domain. And so at every point P along the path, there's something called a unit tangent vector, which is denoted by uppercase T. And if you're looking at the unit tangent vector at a specific point, it's going to have a subscript P. So this unit tangent vector is going to point in the direction of the motion of the parameterization. In other words, it's going to point in the direction of the velocity vector, but it's going to have unit length. And so by definition, if we write, we're going to write like the unit tangent vector with respect to the parameter t for the unit tangent vector. And then by definition, the unit tangent vector is just going to be given by the derivative of your parameterization divided by the length of that vector, right? So like this is saying this is the velocity vector or tangent vector, same thing. And then you, to normalize it, to make it so it has length 1, you just divide by the magnitude, right? So this is something we've already seen before in this class. And so just as a quick example, this next one wants you to compute the unit tangent vector, t of p, at p is equal to 1, 1, 1. If we have that r of t ends up being equal to t squared, and then t cubed. So I guess the first question you want to ask yourself is you want to determine for what value of t are we going to be plugging in to this unit tangent vector in order to find the unit tangent vector at p. Does anyone see what value of t we need to plug in order to make it so we get like a corresponding point of p is equal to 1, 1, 1? Does anyone know? Yeah, so all you would have to do, right, is we want, like we're given r of t is equal to t squared, t cubed. And in particular, we're interested in the point p is equal to 1, 1, 1 on our curve. So all you do is just set this equal to one another. So t squared, t cubed is equal to the point 1, 1, 1. And then you just need to solve for t, but it's immediately just determined by the first component, right? Like we have to have t is equal to 1. And I mean, that means t is equal to 1, and that's all there is to it. So this implies that t is equal to 1. Right, when t is equal to 1, we get the point p is equal to 1, 1, 1 on our curve. And so what we need to find is the following. So we ultimately want to find the unit tangent vector at this point. So we need to find the following. We need to find t, the unit tangent vector at p. By definition, this is equal to r prime evaluated at 1 divided by the magnitude of this vector at t is equal to 1. Okay, and so from here, it's pretty straightforward, right? You just need to compute some quantities, right? If we want to find r prime is just going to be 1, 2t, and then 3t squared. And then all you have to do is just plug in t is equal to 1. So this will give you the vector 1, 2, 3. And then all you have to do from here is you just need to divide by the magnitude of this vector, right? So you just divide by the square root of 1 squared plus 2 squared plus 3 squared. And so this is the square root of 14. So this ends up giving you the vector 1 over the square root of 14, and then times the vector 1, 2, 3. So this is how you compute the unit tangent vector, right? Again, all you really have to think about is you just compute the derivative, and then you divide by the magnitude of the derivative to make it a unit vector. So it should be pretty intuitive, this idea. And of course, like the computation generally isn't so bad either. As long as you can compute the derivative, it should be pretty straightforward. Any questions about this example? Okay. So before finishing class today, I only have a couple more minutes. I just want to relate like how the unit tangent vector is going to show up in computing curvature. And so now we're going to imagine we're going to be following a path, and we're going to observe how the unit tangent vector t changes direction, as in the figure on the next page. Right, so ignoring the box that we have here, which gives you the definition of curvature, like say we have this curve right here, we're interested in looking at how the unit tangent vector is changing direction over time. So it's completely independent of the speed that you have, right, is the main point I'm getting at. And so like the curvature is large where the unit tangent vector changes direction rapidly. So how do we measure this? So a change in t indicates that the path is bending. And the more rapidly t changes, the more the path is going to bend. So with this in mind, naturally you'll think that one way of computing curvature is it's going to be by computing the magnitude of the derivative of the unit tangent vector with respect to t. And this seems like it would be a good measure of curvature. But again, the main issue we're going to have is that this derivative can value, like its value could be changing with respect to the magnitude over time, right? So like this quantity, like this magnitude is going to depend on how fast you end up walking. So the faster you walk, the faster the unit tangent vector is going to change. And we want to be completely independent of this speed or like how fast you're going to be walking, right? And so this is where the arc length parameterization comes in. The reason why we define the arc length parameterization is to make it so the speed doesn't change over time, no matter where you're at in the domain. So instead of taking the derivative of the unit tangent vector with respect to t, what you want to do is you want to take the derivative of the unit tangent vector with respect to the arc length s instead. Right, so with this in mind, we assume you walk at unit speed. In other words, the curvature is going to be the magnitude of the derivative of the unit tangent vector with respect to s, where s is the parameter of an arc length parameterization. Right, so this is summarized at the top of the next page in the definition. So if we have that r of s is an arc length parameterization and t is a unit tangent vector, the curvature of the underlying curve at r of s ends up being the following quantity. So you take your unit tangent vector parameterized by s, you take its derivative, and then you compute the magnitude. So there's actually a lot of steps. Like it looks really simple, but there's actually a lot that you need to do to compute this, right? You need to find the arc length parameterization, you need to find the unit tangent vector, then you need to compute a derivative, and then you need to compute the magnitude of that. There's like 4 steps, and then like in each of those steps there's sometimes like multiple steps, so this is like deceptively simple. In class tomorrow we'll go through an example of like how to compute the curvature, and in general we'll find another way of computing the curvature that will allow us to bypass like the arc length parameterization, which will be more convenient later on. Okay, any questions before I end class? And again, if you have questions about the homework, I'll be in my office from 2 to 4.